So let's get started. Yeah. So let me presentation mode. Yeah. So last week we discussed about the basic concept for DC motor. I know many of you already know briefly. So for DC motor, we have armature current, which is main winding. We call armature. Another one is magnetic field winding. We provide the magnetic field. So the magnetic field we can use in PM, so-called the PM motor, permanent magnet motor. We can also have separate winding, provide us with the way to provide a magnetic field. So, but the power for the magnetic winding should be somewhere. We can either use a separate power source, external control unit, or we can do it together, say in this one, in parallel with the main current, main power source, we call it shunt. Or we can put them in series, or sometimes we can split them, become series and pair. So either method has some advantage, disadvantage. You can see that in here, that will be easy enough, but however, this current, field current, will same as the armature current, so the conductivity will be less good. Here, then of course, the voltage will be controlled. So if we want to control the armature voltage, we also control the field. So that's not that nice to have. So here will be also a combination. So this one separate control that is much better. We can control whatever magnetic flux we like to be. So we separate control the armature current. So in this case, armature current is similar to the magnetic field or similar to the torque. The torque current among the torque is controlled by this current. So we can able to use this source to control torque, or we can the field here. We can also assist them with different kind of the speed range. So that's why by using field current, you can also control the motor in different type of operational range. So that's nice to have that. So that's to say you can control torque, you can control the speed by using separate controls. This method is simply better, but you need to separate power source to do that. So that means if PM motor, we have difficulty to control the magnetic flux. So in this case, the frequency range or the speed range will be also narrowed down to a certain range as well. So here you can see that we further discuss about the different type. About the shunt will be just the voltage cannot be separate control because the voltage for the winding is the same as the armature winding. So that to say, if you want to increase the armature voltage in here, then this also increase that this something we don't quite like the magnetic flux is uncontrollable. So cumulative is combination of these two. Therefore, if this voltage control this field, we can also using this voltage control the total voltage for both the motor armature and also the field winding. But actually, the separate exciter are more commonly being used. So, but for history of development, for some simple motor, we still have the other three. Then here you can see that the comparison among different kinds of the motor. So in shunt motor, it highly depends on the load. So that means when the load change, maybe even though the torque change, then it also have some variation as well. But the thing is, what we like to do will be we can able to control the torque and the speed quite separate, and also have wider range of the variation. So that's why separately excited motor, which and like that, you can able to control the torque and also the speed in any one of the manner. So that's to say, if you want to control the speed at this one, you can control all a wide range of the torque. But for the other type motor, like series motor, if you want to control the torque, but the torque cannot be controlled in any range, like the high torque, you only have lower speed and vice versa. So that's why we usually prefer to have a separate exciter, because for any speed, for this particular speed, you can able to control wide range of torque. Of course, this doesn't mean we only have single speed. This means we are able for some particular speed that can be wide range of torque. And for this separate excited motor, we can have different kind of the speed profile. So that is to say, you can do whatever you like. So that means for that separate excited motor, usually will be much better capable. You can do a lot of variation for the speed and torque. So initially, most of the EV development are based on this separate excited DC motor. Because we are able to adjust the motor current, which is the same as the motor torque, and also motor speed by the field winding. So that's to say this kind of separate motor are now being common used and more common for all the DC system, DC motor system. And this all called the one field and the PM are conventional. You see PM conventional, the first motor being developed also using a PM. They use some magnet, they put a winding, the motor will have the rotation. But the first motor being developed is PM. So really conventional, and later on, they have used a separate winding to provide the field called one field motor system. So that's what, however, this kind of motor is still a commutator and a brush for change the direction of current so the motor can continue to rotate indefinitely. Without a commutator and brush, then we have difficulty to do that. Oh, it's a spelling mistake, not commutator, commutator. Commutator. So anyway, the commutator and brush is more good because it can able to provide us with the spike current. Once the commutator there's some contact issue, we need to separate the current to change to another 180 degrees. So that's why this kind of separation of current will provide us with the spike, and sometimes the commutator will have the friction due to the contact point. So that also is not that good. And also EMI, whenever there's spike, it will produce us with the electromagnetic interference. So that is something affecting the rest of the electronic system. But that's why for the modern EV, we tend not to use them. So all the EV, you can see that we don't use this kind of the simple DC motor. Commutator is no good because of the spike and dynamic performance. Last week, we also show you a table of all the EV, what motor they are using. You can see that only really old model are using this kind of the commutator and brush motor system. And then next thing is to see, we still need to go through some simple mathematics. Some of you may have learned the DC motor equation. I know some of you may have learned that. Who has already learned that? DC motor equation? Of the gentleman in the middle, you said you already learned sometime long time ago. So that's it's a quick revision. So just in case you need to understand more about it. So basically, motor, we can have applied motor voltage in here. We apply the motor voltage here. But inside motor, we got two items. One will be the back EMF E on the winding. Anything excitation in the winding, there's some back EMF. That EMF is trying against the input voltage. Otherwise, we have too high voltage applied to the winding. You see a motor winding, just coil or copper conductor. If you don't back EMF, you see you can more look like a short circuit. So that's why once the motor starts to rotate, this will become a voltage. And then to against the original applied voltage, then it can be due to actual current pass through. So that's why in the motor equation, we got the E here is the back EMF, which is generated against original voltage. And this RAIA is the voltage drop due to the current. IA is the current pass through the motor. We call it A is means armature current. So this is copper winding. Of course, you got some resistance, but that means the equation will simply voltage equal to this internal voltage plus the voltage drop on winding as this. And it happens to be, we know that the back EMF are nearly proportional to the speed or medium 2πf, the rotation speed of the motor, and then that's a constant, K constant. And the amount of torque, as I mentioned, current is highly related to the motor torque. So that is to say, this current is proportional also to the torque. We happen to be these two proportional constant and equal, I think, in the even when you go in the undergraduate, we learn how to define this equation. We can define that this K constant and equal for this equation. But anyway, based on that, there's a really basic equation for motor system, for DC motor system. So usually in the undergraduate electrical machine, you should learn this equation. And then now we try to connect this motor to a motor drive system. Let's see how and develop a two quadrant, meaning a two version of the operation. So usually this kind of motor, we energize them, we provide power to it. And then we can also think about if we want to loop this current are moving in this direction, we can continue to loop over this thing. Or we turn off this current, we can therefore return to the battery. So this is another way. So you can see that this is two operation domain for the motor. But of course, we can merge them into single circuitry between this one. So that's to say, you can see that if you turn on this transistor, we are now putting the current into here. Or if you turn on this transistor, this current can also looping in here. We can therefore control duty ratio. How long it turn on, turn off. We can control how much voltage will go to the motor. We can also control if there will be any power regeneration. So that's the circuit. So this circuit, we call it half bridge circuit. It's also very popular for the half bridge circuit system. So we call it half bridge. So that means if a transistor using this format. So this is our half bridge. That's our electrical engineer, how we say this kind of the jargon. So, and one typical question will be, sketch the current under quadrant 1 when the transistor on and off. Which transistor is responsible for quadrant 1? Probably you may not understand properly. Let's so go for the answer. So quadrant 1 did mean we are motoring. We are using a battery or a power source to motorize the motor. So that means we're putting a positive voltage to the motor to energize the motor. So we turn on this one and turn off this transistor. This is very straightforward. Just like if you learn anything about the buck converter, then it's the same. So, then let's think about quadrant 2. If you've forgotten quadrant 2, that's okay. Let's go through the tutorial, then you know what quadrant 2 is. So which transistor is responsible for the quadrant 2? I don't have answer here. Anyway, so quadrant 2, what's the quadrant 2 mean? You go back to the previous case then. So, and power regeneration and forward braking. So that means for the quadrant 2 operation, then we can see that let me get a pen to sketch dimension on here. Then we want to reduce the motor current, reduce the speed. How we can do that? So that means if we're able to, then the motor current is still flowing in here. So if you turn on this transistor, the current will looping in here, continue loop. Although this is not breaking really well, but we can able to loop the current in here. So that, so that's one way we can force the motor current to confine this loop. It's not supplying the current from the power source. then in this case, the top transistor will be off, and then the bottom transistor should be on. Let me erase. Okay. So that's to say the waveform will be like that. So we are using on-off switching waveform to energize them so that we're able to control how the motor voltage appear. So that means if that's the voltage, so we can turn on to control the top transistor, how much on time. We can therefore apply voltage to the motor to be controlled by top transistor, or how much turn on time. You can see that if you go back to this here, you can see that once we turn on the top transistor here, the motor voltage will therefore equal to this voltage. So that means this turn on time will be control how much voltage. You see magnetic coil, they don't understand about voltage and time. They only use an average voltage and time, because that's so-called the flux linkage. I'm not quite sure you know the term. So that is to say, the motor will try to understand how much voltage or how long the period of time will be important for motor to determine its torque and energy. So that's to say, we apply the voltage for certain term on waiting time, VB voltage, with certain duration or operation, then you give you how much average voltage go to the motor. So that is how we understand how the motor actually operates. So that's to say in here, if you turn on the motor, with this turn on time, this turn off, so this two ratio, average will be somewhere in here. So that will be the average voltage to the motor. So that means some of the control method for the motor to control how much voltage for the motor, we can just fix down time. And then that will easy just look like a monostable fixed down time, but we can also variable the frequency. The frequency can be varied. For some of the people, they may also using the pulse width or vary, and most of the time are vary. Some people they may control using fixed frequency, and then we can change the pulse width to control the voltage. So many different ways we can control them. But of course, for me, I usually will use fixed frequency because it's easier to control. Because for this one, we only control the so-called ratio, this ratio here, and then the frequency will be fixed. Then in terms of the metric, the harmonics, then we know the frequency always within this time period of the frequency, easier for us to design a filter. If we are using variable frequency like this, we're not quite sure where the frequency range, and then we have difficulty to design the filter. So that's why for Panasonic or each vehicle, then we tend to use this method.
Yes. How do you specify the frequency, like at which range?
Yeah, that's a really good question. That depends on power level. As you see last week, we mentioned to you, we got many different transistors. If we use, say, IGBT, the frequency range for IGBT can be usually about from DC up to 100 kilohertz. For MOSFET, from DC up to 1 megahertz. So use a high frequency, the better the operation. Then, so that's why it also depends on power level. This 100 kilohertz doesn't mean always be 100 kilohertz, because the losses, you can see that the losses here, lower losses, the losses here will be higher. So even though you can able to work 100 kilohertz, but doesn't mean we like to do that because you can create more losses. So that's why we need to make a compromise. You see for a motor system, if your motor 100 kilowatt, if these losses cost you about, say, 10 kilowatt, this only costs you about, say, 0.5 kilowatt. Then that will be critical. If your motor running at 100 kilowatt, then you see 10% will become the power losses. So of course, if a 100 kilowatt, I may not select 100 kilohertz for the switching. You may select something like in here, so that the efficiency can be more sensible. So that means that to say, if for a very huge system, large system, then probably we will prefer to select low range, because for too high frequency switching, we need to switch high current, high voltage, the power loss will become higher. So the rule of thumb will be, we usually for high power, probably usually maybe 20 kilohertz up to 50 kilohertz. Sometimes can be as low as 10 kilohertz. For low power, then will be something opposed to 100 kilohertz or beyond. Yeah. So today, for most of electric vehicle, the switching frequency for inverter and roughly about 50 kilohertz, not really high yet, because we still need a high performance transistor to do that. And then you can see that, for example, for powertrain, for train, cross-country train, the power level is megawatt. Of course, we cannot use 100 kilohertz, only about 20 kilohertz, maybe 10 kilohertz. Yeah. That mainly is the power level problem. So this is a characteristic for the torque speed characteristic. Many people have learned that in the past. What this curve means, all the motor have a base frequency, and then you can able to use torque controller to control this torque to be really linear for a wide range of the speed, from zero speed up to the base speed. So that means in the standstill, you are able to have full amount of torque. So that's why EV, you can able to start accelerating much better than gasoline car. And the torque multiplied by the speed, according to the linear increasing. So up to one limit, we cannot further increase with the power, because power rating of motor is fixed. If you use 100 kilowatt motor, so this point, you give the torque multiplied by speed become 100 kW, so that's maximum torque or power. That's it. And then, but however, motor also allows you to overdrive over the speed. If you want to carry on all over it, what you need to do will be the speed is increasing. Of course, your torque cannot be increased further, because torque and omega is the power. The power equal the torque times the omega. I think we all know this equation. So when you want to go to overdrive high speed, then this must be decreased. So that's why you can see that the torque ripple will therefore decrease. But that's quite okay. Same as when you're driving your gasoline car, you can see that in the highway, when you drive at 80 miles per hour, you don't need that much torque. Yeah. So I mean, because the friction unit time will be less, you don't have that much static force requirement. Of course, if you drive to further high speed, you will have a high driving force. That will another manner. So that means your car cannot accelerate indefinitely in certain range, then you can able to overdrive. The high range, you can't do much about it. So that means your car usually in this range will be, say, from 0 to 50 km per hour, and then when you overdrive, your torque will drop. So this curve, this characteristic is very famous. All the motor will have this kind of the characteristic. So another one would be 4-quadrant drive. 4-quadrant drive, you can see that we have to use more transistor. So basically, we can have more controllability, allow the motor to run at any direction or rotation for braking or power regeneration. That's what we try to do. You can see that this motor sketch the 4-quadrant drive, or done that, sketch the current path in the third quadrant when the motor, which transistor is on and off. Third quadrant means motor become reversed. So for instance, if you energize this motor, forward movement, but positive voltage in here, the motor will rotate forward. Like that. In theory, we can reverse the voltage, become reverse motoring. That means to reverse the input voltage. So what you need to do is turn on these two transistors, then the motor will become reverse voltage. So that's why for using this one, we have many operations we are able to do the changes. Oh, so for instance, let's do. So this is the motoring, yeah. You can see the possible voltage, yeah. And then if we want to do the reverse, like the third quadrant, let me see if I'm able to change the color. Third quadrant, then I can turn on this two, like this. Then we posting this pulse voltage on here, then we therefore reverse the voltage. And then if we want to do the power regeneration, then let's say erase it. Yeah. So power regeneration, that means originally the motor is, the current is flowing in this way. Oh, sorry. And see the current is now flowing in this way. Then originally is from here. We power up the motor. But if we want to power regen, what we need to do is turn off these two. But if you turn on this, and then we turn on this one, change the red color for power regen. And then we turn on this two. So what do you do? This current still flowing in the motor cannot suddenly disappear. Yeah. Okay, we just turn on these two transistors, and then become power regen. So what happens in the when you drive an EV will be, when you're motoring, then the blue color will operate. Color blue. With that motoring. Regen braking. Like that. And so it's very straightforward. Quadrant control is best. All the EV are using 4-quadrant control. Low when you use 2-quadrant, 3-quadrant. No, that's a standard circuitry. So you can do forward, reverse, regen, whatever you can do with here. Very straightforward, quite simple. So that means when you drive an EV, when it has the gas button, then first you go to the motoring. And then for Tesla, we can release it. Then we therefore go to power regen. So what they did is turn off this tool. And then this current will therefore automatically can flow through the diode. The diode will automatically turn on because forward current, this current will flow through this. Even though you turn on this transistor, you can still able to do that. Then you automatically become the regen braking. So that's why when you drive a Tesla, when you just release the gas, then you can see the vehicle getting slowed down and brake and stop because of this kind of the function. Okay. And then when you change to the reverse, then you just turn on these two transistors all the time. Then you can therefore reverse the motor to the reverse side. So that's why you can use 4-quadrant control to control everything. And that's how we do the braking, how we do the power regeneration. And then for the EV, that's the two better ones, the brake. The gas button is also with the motoring and power regen is controlled with this one. And then the braking there, two types of the design. Say Tesla, they will put the mechanical brake on the left-hand side. So it's really good in mechanical brake. And then there's still some power regen braking. They still allow the current to flow through back into the battery, but simultaneously they have the regen braking plus the mechanical brake, the disc brake there. And then for the right-hand side button, motoring and also power regen. So that's how they design the car. But for the other EVs, say for Leaf, then they design it differently. The first half will be the whole gas pedal will be for the motoring. And then for the braking, they have two halves. The first half will be power regeneration. Second half will be ensured with the mechanical braking. So that's why all the EV design are slightly different. If you drive EV, you know that for Tesla, once you release the gas button, release gas pedal, you just start to brake. But for Leaf, it's quite different. When you release it, you still have some kind of the power to go forward. Once you press the brake button, then you start to stop. Then that will actuate for your regen braking plus your mechanical braking. So you can feel that you can do anyone driving my EV. So you can try that. After you drive, then you know what I'm talking about. Anyway. So to conclusion, what we discussed in this chapter, we say DC drive is one of the really basic drive for motor system. Still used in many kind of applications. They're really good way to control motor also. And basically, we can say separate excited, shunt, series, and commutative one. But most popular, of course, within the separate excited one. All quadrant drive is now commonly in use. Although in technical paper or in literature, we still show you about first quadrant, second quadrant, third quadrant. There's low use motor, nobody will use it, only for paper study. We never use them. And four quadrant drive is a standard drive for all the electric vehicle, for all the motor. It's also called the H bridge. On curve side, look like an H, two sides. So that's why it's called H bridge. This is called the half bridge. When we have both, we call them H bridge. So that's how the technology being used. So there's some reference if you like to check more. Okay. So next, any question up to this point?